Thank you, sir. Good day, everyone. My name is Peter Mfonobon Kweso. I'm a student of Tempers Research Institute under the tutelage of Dr. Yaki and research assistant to Dr. Chika at the University of Lagos AI and Robotics Laboratory. Today, the paper I'll be presenting to you will be on special functions, specifically the gamma and beta functions. We are going to be looking at the definitions of these functions, as well as its relationship with other formulas, which help better define them. We'll also delve into its properties and applications in various fields. Special functions in general have a lot of uses across various fields. For instance, in economics, the gamma function is used in modeling income distribution, as well as the utility function. We see in physics, the Legendre function is being used in quantum mechanics, as well as the Bessel function, which is used in signal processing. Each of these functions have their own distinct properties that make them different from these elementary functions. For instance, the gamma function in its recursive nature, which can be seen in its duplication formula, as well as its relationship with the beta function, sorry. Each of them have their own uses, and they are very important in solving complex integrals or complex equations, I may say. Let's look into some of these definitions. The gamma function, defined by gamma m for all m which are in the set of natural numbers, is equal to m minus 1 factorial. It can be expanded to the complex realm as follows. The definite integral of 0 to alpha of x to the m minus 1 e to the x dx, where m is greater than 0, and the real part also has to be greater than 0. Another way we can describe the gamma function for complex number is through the Weierstrass product theorem. This can be seen as follows. 1 over gamma m is equal to m times e to the lowercase gamma m for the summation of the products of p1 to infinity of 1 plus m over p dot e to the power of m over p. Here, the lowercase gamma is the Euler-Mascheroni constant. This helps us to shift the starting point of the gamma functions to accommodate more values of the functions. Also, the beta function denoted by beta m on m can be defined as the definite integral of 0 to 1 of x to the n minus 1, 1 minus x to the n minus 1 dx. Each of them have their own properties that we'll discuss as follows. Property 1. We know that the gamma function cannot exist for all m that are in the set of integers less than or equal to 0. We'll prove this by contradiction. Let's assume that it is true for this set, and let's pick a random number in this set. For instance, here is m equals to 0. So when we plug into the equation, we get that the gamma of 0 is equal to minus 1 factorial. And minus 1 factorial is undefined by definition. So that means gamma of m cannot exist in the set of integers less than or equal to 0. The next property we are going to be proving is that gamma of m is continuous for all m in the set of natural numbers. There are some things that must be followed before a function can be continuous. For example, it must lie within that set. That means for every value of gamma m, it must be a natural number, as well as the limit must exist for m to a particular number that is less here as in a. And the limit must also equal to this function, which is the gamma function that we're dealing with. We'll prove this through induction. We first show that it's true for gamma 1. Doing this, we get that gamma 1 is equal to 1. Then we have to now assume that it's true for m equals to k. Let's just say that m equals to k is true, so that we can prove that it's true for m equals to k plus 1. When we do this, we see that the gamma function, gamma k, equals to k of gamma k, that f of k plus 1 equals to k of gamma k, sorry. So here now, we have a distinct property of the gamma function, that gamma k plus 1 is equal to k of gamma k. So this now, we know that gamma of k, as we have already assumed, is admissible for all m elements of natural numbers. So we also know that k as well is a natural number itself. So that means k times gamma k should also be in the set of natural numbers. That is proven. So here we also prove that its limit exists. We first need to know that whether the integrand of this gamma function, x to the m minus 1 e minus x, does the limit exist. Once we show this, we can use through Kamishagi 2020 and the dominated convergence theorem that the limit actually does exist. In the process of solving this, we see that the limit of the gamma function is equal to the gamma function itself. Once we have done this, we have proven that the limit exists and is also equal to the function itself. The property 3, the gamma function for all m elements of natural numbers is monotone increasing. To prove this, we are going to show that first is an element of natural numbers, which we have already shown before. And we now have to prove that for every m2, m1, where m2 is greater than m1, that gamma of m2 is greater than gamma of m1. So we'll prove this through contradiction. So when we do this, we can take that m2 is equal to m1 plus b, and using the fact that gamma of m equals to m minus 1 factorial, we know that m2 minus 1 factorial is equal to m1 minus 1 plus b factorial. Then by using the formula, we have that m1 minus 1 plus b factorial is equal to m1 minus 1 factorial into the combination of m1 minus 1 plus b to b. So now all we need to prove is that this combination here is greater than 1. But we already know that m1 and b, they are both natural numbers. That means m1 plus b minus 1 is going to be a natural number, and b as well is a natural number. So we have already known that this one has to be greater than or equal to 1. So when we do this, we clearly see that the f of m2 is greater than f of m1. That means it's increasing. Next property we are going to look at is this duplication formula. This r, the gamma of m into gamma of 1 minus m is equal to pi over sine pi m. We are going to do this using the Weierstrass formula. When we do this, when we plug in this value into the Weierstrass formula, we get the following equation. So we now have to replace gamma of minus m with gamma 1 minus m over m. Solving, we get m to the infinite product of p to 1 to infinity of 1 minus m squared over p squared. Then we now put that, we know that the fact that sine pi m equals to pi m of the infinite product p equals to 1 to infinity of 1 to m squared over p squared. Then on substitution, it gives our required value. Also, we look at the beta function. Let's look at one of its formulas. One is that beta m, comma m is equal to beta n of m. So we'll start here by defining what beta n of m is. And from follows, we can see that it's definite integral of 0 to 1 of t to the n minus 1, 1 minus t n minus 1 dt. Once already we see this, we already see that is a kind of a link here. I'll show. For instance, we know that for a definite integral of 0 to a, f of x is the same thing as 0 to a of f of x of a minus x. So all we have to do is just put 1 in front of each of them, subtract each of these terms, t and 1 minus t by 1. Once we do this, we get a similar equation to the original gamma function, which is beta m, comma m. Next property we'll be looking at is the trigonometric form of this gamma of the beta function. Sorry, we can represent it in terms of sine and cos. All that's needed to do is replace the value of t with sine squared theta. All the other calculations following from this prove the trigonometric form of this. The seventh property we're looking at is the summation of beta functions to give the original beta function itself. So you know that beta m, comma m plus 1 plus beta m plus 1, comma m has to equal to the original beta function, which is beta m, comma n. All that the proof here is just through the definition of each of them. When you add them together, you get that it's actually true. The next property is the relationship between the gamma and the beta functions. So beta m of n is equal to the product of gamma m and n over the summation of the gamma of m plus n. This is done when we're solving this. We have to change integrals because we are trying to express it in a term that will see the gamma function inside. So when we do this, we are going to pick the change of variables u equals st and v equals to s of 1 minus t. So since there's going to be a change in the states of this stuff, because there's in the third dimension, there's going to be a shift inside or a difference in space occupied by this function because of this change of variable. We now have to calculate for the Jacobian. When calculating the Jacobian, we get that it's equal to s. So on solving, we will get that the gamma function, gamma m times gamma n is equal to beta m of n times gamma m plus n. So all we need to do is divide both sides by gamma m plus n, and we have gotten our solution. Let's look into its applications. We see that the gamma function and beta function have applications in the field of factorials and combination. For instance, it helps us to expand the factorials to non-positive numbers, or for example, -1/2 factorial. From here, we know that -1/2 factorial is the same thing as gamma -1/2 + 1, which follows from gamma m plus 1 equals to gamma m minus 1. So that's just what is here. Once we do this, we know that -1/2 factorial is the same thing as gamma 1/2. So using the duplication formula, that is gamma m times gamma m1 minus m, we know that it's equal to pi over sine pi m. So letting m equals to 1/2 in the equation and putting in the equation, we get that gamma half is equal to √2, which has proven that -1/2 factorial is equal to √2. Here we see something.
Sorry for interrupting you. Can you please show us the duplication formula? Can you show us again? Let us see the duplication formula so we see how you are applying it. Can you go back to the previous screen, please? So you show us the duplication formula, and then we can see how you are applying that to computing the factorial of a negative real number that is not an integer.
Okay, I'll go back to that. Let's see. My screen is okay. So from property 4, we know that from here we can see that gamma m times gamma 1 minus m is equal to pi over sine pi over m. So what we're going to do here is replace the value of m with half. When we do this, we get gamma of half times gamma of 1 minus half will be equal to pi over sine pi over 2. From here now, we see that this and this are the same. They are both gamma half. So all we do is put gamma half all square, and it's equal to pi over sine pi over 2. And we know that sine pi over 2 is simply 1. That is sine 90. So that means the gamma for half of gamma all square is equal to pi. When you square root it, you get a gamma half. Is equal to the square root of pi.
Yeah, thank you. Yeah, that's clear.
Okay, you're welcome. So let's go to the next property. Let's go to the next property. Sorry for screen is holding on. Okay. So we're proving that gamma half or -1/2 factorial is equal to the square root of pi. Next, we'll look at its application in statistics and probability. In statistics and probability, the gamma function is applied mostly in the gamma distribution as well as the beta distribution. We see in the gamma distribution defined for a random variable x as f of x equals to 1/gamma m times theta m times x raised by m minus 1 e to the minus x over theta. Here, x has to be greater than 0. So x is the random variable, is a specific waiting time. M is the shape perimeter. It determines the shape of distribution. For larger values of m, we see that the waiting times that we are required are longer. And theta is also the scale perimeter. This helps us control or determine the durations of the waiting time. So now, what we're going to see here is the applications of this in the formulas. Like for example, to prove that the PDF of the gamma function itself is going to be 1, which is a common property of PDF, as well as proving the moments of the random variable x under the gamma distribution. Let's look into that. So first one, we know that the PDF of the gamma function has to be 1. That is what we are going to prove here. So once we plug in,
why do we have the limits going from 0 to infinity? Why not this? This looks like why are we having a limit from 0 to infinity? Because
a limit of 0 to infinity.
Yeah, the limit, yes.
Yes, because that is the range at which the gamma distribution works on, at which the gamma function works on.
Okay.
From 0 to infinity. So here the PDF also has to work within its range so that it will be applicable.
All right.
So now what we are doing is we're going to put it into the equation, the PDF of the gamma distribution. Once we put this in, we'll get that the gamma function 1 over gamma m times theta raised by m into times the definite integral of 0 to infinity of x to the m minus 1 e to the x over theta dx. This formula here resembles the gamma function in a way, but not completely. So in order to fix this, we have to make some substitutions. So here now, what we'll just do is that we'll let u equal to x over theta. Once we make this substitution, our integral will now become the definite integral of 0 to infinity of, since u is equal to x over theta, we know that x is going to equal to u theta, meaning that x to the m minus 1 is the same thing as u theta to the m minus 1.
The proper integral is a definite integral.
Sorry. So substituting this into the equation, we have u to the m minus 1 and theta to the m minus 1 times e raised to power u. Then the differential of dx will change from dx to du times theta. So once we do this now, we know that our right-hand side, the left-hand part is 1 over Rm into theta raised by m. So from here now, we see that the multiplications theta and this will cancel out theta raised by m. So we're left with 1 over gamma m into the definite integral of 0 to infinity of u, s times u to m minus 1 e to the negative u du. And we see that this now is the same thing as gamma of m, which on multiplication will subtract this and this, which makes our equation equal to 1. So that shows us that our equation is equal to 1. Let's move to the next proof. Here we're going to prove the first moment of a random variable x under the gamma distribution is equal to m times theta. The first thing we need to know here is that the expected value of x.
Can you tell us what moments are?
What the moment is?
Can you explain to us what is first moment? What does that mean? Because some of us are not statistics people, so we need to know what these moments are.
Okay. the first moment of a random variable or the expect is also known as the expected value of that random variable or the mean of the variable. It helps us to determine the mean of the random variable. That's what the moment is. It's the mean of this random variable. That's just what it is, the mean. So here now, we're going to look at the formula to get the expected value of the random variable x. So here the x is not the one specific waiting time, but the generalized random variable x for the gamma function, for the gamma distribution, sorry. So we know that the formula for the expected value of x is equal to the definite integral of 0 to infinity of x times f of x dx, and f of x is the PDF of the gamma distribution. So from this formula, we're going to put in the gamma function or the gamma distribution inside. So following what we already did initially, we know that this will become, that is from substituting that u equals to x over theta. We know that the function, it's the function will become the gamma function of infinity to 0 of x m dot theta m dot e to negative u and theta. This is the same as this, following from our proof of the PDF of the gamma distribution. So what we see here is that theta and this will cancel this, making a remainder now theta over gamma m times, here now we see that this resembles the gamma function as well. But what we see here is that instead of m minus 1 as the original, is now m. So the gamma function will change from being gamma m to gamma m plus 1. So now it's going to be gamma m plus 1.
Sorry for interrupting you. Sorry for interrupting. Can you go and show us the definition again of the gamma function so we can see how the m plus 1, how it came about? Yeah. Okay. So the main definition itself of the first one. So we can see, why you are saying m plus 1. Because it's supposed to be gamma.
From here, yeah. So from here now, we know that the gamma function can be defined as follows. Gamma of m is equal to the following: the definite integral of 0 to infinity of x to the m minus 1 e to the x dx for all m greater than or equal to 0, where their real part is 0. So now we know that this function is x. Here, instead of being the function, instead of being x to m minus 1 as of here, is now x to m, which implies that the gamma of m here will have to add a 1, which is gamma m plus 1. Okay. That is what we have shown.
Sorry, also just while you're there, in equation 3, why is the m for the equation 3? Is there any reason, like, if you restrict the m to the natural numbers like you have in 2, Malik, hold on. So can you see that, like, is there any did you use 3 anywhere?
Did I use 3? Yes, I did use 3. That was in the proof of the duplication formula. Should I go over the...
No. I just want to, but you restricted it to, m to natural set of natural numbers and not on complex numbers, because I haven't seen you use complex numbers in the talk.
Oh, in the proof.
Yeah.
Okay.
Like, is there any, yeah.
There's no reason for not using
Okay,
complex
good.
numbers. It was not just applied in the scope of study as of now.
Okay, all right, all right. All right.
Yes.
I just wanted
But
to bring that to you.
Yeah,
okay.
and
But
I
you
think
understand, you
every
understand.
real number is a complex number, but not all complex
Yes,
numbers are
I
real.
know, but I know where it's coming at. He wants an I or something.
No, but I
I
just want to make sure that you know that
Exactly what
3
you're doing.
is more general than 2, yeah.
Yeah, exactly. Than to the
Yeah.
natural. Yeah, that's correct. Yeah.
Okay. Okay. So let me continue from that side. So from here now, we know that y is gamma m plus 1 instead of gamma m. So we'll use a special formula of the gamma function that we made note later on. For example, in this proof, we know that f of k plus 1 is equal to f of k. Let me highlight it out for you. That's f of k plus 1 is equal to gamma of k. So that shows us that, sorry, let me put it back. We know that f of k plus 1 is equal to gamma of k, right? That is what we're going to use next. So implying that once we have a gamma 1 over gamma m, that is theta over gamma m, sorry, over gamma m times gamma of m plus 1. It will become theta over gamma m times m of gamma n, which on solving will arrive at our desired result, m dot theta. Yeah, so that is what we're going to get. So let's go on to the next proof, which is the second moment of variance, as some may call it. So the second moment of variance defined by var of x is equal to m times theta squared. We now use the fact that the var of x is equal to the expected value of x squared minus the mean all squared. When we solve it, we already know what the expected value of x or the mean of x is, which is m times theta. Now, what we really need to find is the expected value of x squared, which is defined as follows. So plugging it in the equation, we get to this familiar integral we keep seeing everywhere. This integral now, once again, can be solved by substituting u equals to x over theta into the equation. When substituting into the equation, instead of getting the usual gamma of m or m plus 1 now, since the power of x has increased by 1, we already expect that the power of the gamma or the value of m of the gamma should also increase by 1, which will now become gamma of m plus 2, as we can see here. So here, we, instead of us splitting the gamma function just once, we'll split it twice. That is from gamma m plus 2 to gamma to m plus 1 times gamma m plus 1, sorry. Which can now be split again as m times gamma m. Sorry if you can't see. So now the gamma of m will cancel out this gamma of m. So I left with m plus 1 and m times theta squared. Solving, we'll get, when we solve it, we'll get our required equation that m dot this m times m plus 1 times theta all squared is the same thing as the expected value of x squared. Now, since we know that expected value of x or mean of x is m theta, that means the expected value of x all square will now be m dot theta all square. So subtracting both of them, we get that the value of x, which is equal to m dot theta all square. Is there any problem with the solution, or do you understand fully? So I'll move over to the next one, the beta distribution. So here now in the beta distribution, the PDF is represented in terms of its beta function itself as xm minus 1 into 1 minus xn over the beta function m over n. Here, x, as once again, is a random variable. M is the shape parameter, as it helps define the shape of the curve and controls the distribution of the beta distribution. And also, shape parameter n determines how the probabilities are spread out and allows their judgment of the parameters for an expected value. I'll show this later on, how n can be used to give us expected values of what we're looking for. So note that when m and n is 1, the standard uniform distribution is obtained. So following from the first one, we are going to prove its PDF once again. And we can prove its PDF by substituting the beta function into it. So once we do this, we have that to compute further, we must introduce the gamma function once again to show how applicable the gamma is. Gamma function is used 20 places. So once we apply the gamma function in again, we have that the integral of 0 to 1 of 1 over beta m of n will now become the integral of 0 to 1 of 1 over gamma m times gamma n. The sum of them. So when we do this, we get that gamma function of m plus n over gamma m times gamma n is equal to the definite integral of 0 to 1 of x of m minus 1 times 1 minus x n minus 1 dx. This whole integral here is similar to the beta function, beta m comma n. Once we put this into the function, we now have to express it once again in terms of the gamma function, which is gamma m times gamma n over gamma m plus n. So this will all cancel out, which will equal to 1. Therefore, we prove that the PDF of the beta distribution is 1. Let's go to the next one, which is the first moment of a random variable x under the beta distribution. So here we know that the first value or the first moment or the mean of the random variable x under the beta distribution is defined as m over n plus n, sorry. So the expected value of x, once again, is x times the PDF of the beta distribution. Solving, following from the first one, we get that the power of m increases once again from m minus 1 to m, meaning that the beta function being used here will increase by 1, which is beta m plus 1. So substituting the gamma function once again, we get that gamma m plus n over gamma m times gamma n will now be multiplied by m times the product of gamma m and n over the summation of m plus n times gamma, summation of m plus n. So this will cancel this out, remaining only m over n plus n, and that is what we are required to find. Let's go to the second moment, the variance. So the variance of the gamma distribution, very long, m of n over m plus n all square into m plus n plus 1. And following that, it is the expected value of x squared minus the square of the mean. We will now compute the expected value of x squared, which from all our m once again increases one more value to x of m plus 1. This. So now this gives us gamma m plus n of gamma m dot gamma n times this is m plus 1 times 1 minus x into n minus 1 dx. Once again, we have to replace it with the beta and the gamma distributions, which gives us our final value. This. So here we'll now go into the final value. So here we'll also look into engineering. In the field of engineering, how is the gamma and beta function being applied? So we see it's applied in reliability function RT, which expressed as P of x less than t is equal to the definite integral of t to infinity of f of x dx, where x or this x represents the lifetime of the system. The reliability function can be expressed using the beta function. But on solving it, we know that the beta function, the limit for the beta function, tend from 0 to 1. But here the limits tend from t to infinity. So when using the beta distribution to solve this, we'll have to rely on the CDF. No, the CDF of the distribution. You have to rely on it. So once we rely on it, we now have that instead of the beta function, instead of the reliability function being expressed in the following rules, it's going to be 1 minus f of t. The f of t is this r of t here, but like the opposite direction. So that is 1 minus the definite integral of t of 0 f of x dx. When we substitute in the beta function now, this is when it can actually work because t will now be 1. You can assume that t is 1. So when we do this, we get our values in terms of the beta functions. So whatever way we want to find the life of the system, it depends on the values m and n we input. So yeah, they can see other applications of the gamma and beta functions in other fields. For instance, in economics, as I mentioned earlier, the beta function can be used to determine the risk-bearing or risk-seeking version of a behavior of a person. The risk-seeking behavior prefers that m is less than n, that the person is willing to take more risk. For risk-seeking, m has to be less than m, as the person is the risk-seeking version. So m is less than n in the gamma function. Once we do this, it helps us determine when a person is ready to go all out to make sure he earns a profit despite the loss that are there. But then there's a risk aversion behavior. That person is willing now, despite the potential gains he might gain from making an investment, he decides not to do that. He decides to stay back and deal with the loss that will be incurred. Here, m is greater than n. This one follows.
Can I ask
Yes?
something?
Yes, you can ask.
In the reliability,
Yes, sir.
Your integral. Okay, no, it's fine. But you are saying that your x. Why should we restrict t to m to equals to 1? Is there any justification?
The justification comes from the application of the beta distribution. The beta distribution only works from 0 to 1. It doesn't work out of that. So once we put in any constant higher than that, we can't assure the values obtained by the beta distribution to be correct.
Yeah, but in the application, what if the application has t greater than 1? Can you apply this to that?
Yes, you can. That is where the CDF comes into play.
Okay, you have to manipulate that to maybe receive
Yes,
it.
you have to manipulate it.
Okay. I'm
Yes.
just bringing you attention to.
Okay. So let's go to the other fields of study. So other area of studies, we see it in astrophysics, modeling the luminosity of stars, quantum mechanics, fluid dynamics, and signal processing, estimating the parameter of signals. For example, there's a signal called the Airy signal, if I'm correct. And in order to do that, you need the gamma function because it helps define an integral that otherwise, using elementary functions, you can't achieve. So despite these functions, instead of me only pertaining to gamma and beta functions, there are other special functions and they have a wide application in multiple fields. They are not limited to one discipline or one area. But from what I've seen, the most of applications of them come under integrals and statistics. Thank you for your time. Please, any questions?
Thank you very much, Ifonobong, for your talk. That was a very brilliant and quick talk. It went so quickly, but actually we have spent 45 minutes or 40 minutes, between 40 to 45 minutes on this talk. Thank you. So the floor is now open, please. If you have any questions, our speaker is happy to answer your questions. So please go ahead and ask your questions. The floor is open.
Please. Let me ask. Okay. Go ahead.
Wait. For the last part, you talk about application, applying.
I'm coming.
The beta function in economics. You talk about risk.
Yeah.
You talk about risk evasion and risks. Risks. I don't know. I forgot that one.
Risks.
But now, what
Risks
does
event.
the
Yes. Okay.
what does the M and what does the M and N stand for? You said M has to be less than in one case and M has to be greater than in one case. What does the M and N stand for?
Okay, so the M and N now, they are like my potential gain and my potential loss from the this entering into that investment. Let's say. So in risk aversion,
Okay.
you know that your sense of being safe, that is M. M is the state where you are safe. You're confident that you're okay. Yeah, you might make a loss from not
Okay.
investing, but like you're stable the way you are.
Okay.
And so once that, sorry,
No, continue.
Okay, so once that
No,
factor
continue.
is once that factor is greater than your risk, like what you want to do, you want to go into it, that M is greater than N. You believe that you're going to face diminishing marginal utility. That is, if you keep on doing more of the investment, instead of making profit, you're going to be reducing from your total utility. So that's what is happening there. Then in the risk aversion now, sorry, that's risk aversion. In the risk seeking now, your M is less than your N, meaning that you're willing to go into more, that you've not gotten your full satisfaction from the investment, that you can do more, increasing marginal utility. There's still a lot more you can do before it finishes up, before you're saying that you're afraid that you'll not make anything again. Do you understand?
Oh, okay. Thank you.
Yeah.
Yes. Yeah, it's okay.
Is there any other question?
Yeah, hello, Mfanabom.
Yeah.
Sorry, please, can you tell us the difference between gamma function, digamma function, and then trigamma function?
Okay, yes. The gamma function, as we know, is the original gamma beta M this. So now when we look into
Please, can
and
you
it's
show us
represented
as you're talking about it, please, can you show us the equations you're talking about so that we can, yes.
Okay. I'm not okay, let me go back. Let me open my whiteboard. Pre opens. Okay, let me just use this. So now let me go to a screen that is clear for us to use. Let me go to a screen that is clear. Okay, let me use here and define it. Sorry, my whiteboard is not opening. I don't know why. All right, let me see if I can open the whiteboard. Whiteboard.
If you can't open the whiteboard, you can as well use this introduction screen.
I can use the instruction side. Okay.
Yeah, you can click on the pen and write on it.
So for the gamma function is what you have defined here, gamma M. So this gamma M is now defined as the definite integral of 0 to infinity, x to the m minus 1, e to the minus x dx. Then for the digamma function shape, that was what you said, right? The digamma function.
Yeah, digamma function and then the trigamma function.
Digamma. I
I need to
believe
know
the
the
digamma.
differences.
Yeah, the digamma function should be restated as this. It's here we're talking about the logarithm of the gamma function, of the original gamma function. That's what the digamma function is about. The logarithm of the original gamma function. It follows from this. Then the trigamma function. Oh, let me see if I can remember it. Because it's been a long time since I read that. But I know
what kind of log, to what base is this logarithm? This logarithm is to
what base.
Yeah, is this a natural logarithm or logarithm to some base?
The natural logarithm.
Natural logarithm.
Yes.
Okay.
Okay. So yeah, that is just the main difference. From the gamma function deals with the function itself. The digamma function is the logarithm, the natural logarithm of the gamma function, which helps us solve it. And trigamma function, I can't fully recall what that was.
Okay, so yes, the digamma function will be, you take the logarithm of the gamma function, and then you take the derivative of that logarithm with respect to the argument of the gamma function. Okay, that would be a digamma function.
Function. Okay.
Okay? Yeah. And then a trigamma function will be the derivative of the digamma function. So that is the second derivative of the log, natural log of the gamma function.
Of the gamma function.
Yeah. So, but let me, I wanted to ask one thing. There is something called the error function. Are you familiar with that? Yes, error function.
Yes.
You're familiar with that. How is that connected to the gamma function? How is the error function connected to the gamma function? Like, I want to know how you can move from since you say you're familiar with the error function, how do you move from the error function to the gamma function? Or how can the gamma function be helpful in working with the error function?
Okay, the error function has to do with the integral from the Gaussian integral, which can be seen in the gamma function as 2 over root pi times the integral of 0 to x of e raised to power minus t all squared. So the error function now, in order to solve the error function, it reaches a point or in the integral where other normal functions won't work, like other normal elementary functions in solving the integral, it will not be applicable. So in order to do this, you have to make use of the gamma function. You have to manipulate this function that you get in order using the gamma function so you can further solve it.
Okay. All right. Then because when you're doing the kind of error function I'm talking about, yeah, you defined the error function correctly. Maybe I shouldn't call it an error function. It's like the Gaussian when you're going from minus infinity to infinity of exponential minus x squared, you know. But that has x squared here. And
yes,
it doesn't have, so how do we use the gamma function to evaluate that?
Okay,
I got my question. Did you get my question?
Just please repeat again.
So it's like saying, how do we evaluate minus infinity, the integral of minus infinity to infinity of exponential minus x squared dx? How do we do that using the gamma function?
Okay, so I should prove the solution.
Yeah, so how can, because you know that particular integral is a very familiar integral in normal distribution.
Yes.
Yeah, I think Dennis can speak more on that. And since it's a very familiar integral in normal distribution, you know, it has some connection with the gamma, and that will lead me to my second question. I have a second question, but can you just show us how to do that?
Okay, the connection e to the negative x squared, right?
Yes, with a limit of minus infinity to
Infinity. Yes, I know.
Yeah.
Minus infinity to infinity. So here now, we know that this function.
There's a dx missing. There's a dx missing there.
Oh yeah, dx. Sorry. Dx. Well, let me make it clearer. So the infinity, negative infinity to infinity of x squared all square dx. Of negative infinity to infinity of x raised to power 0 e raised to power minus x squared dx. So here, what we'll do is that we are going to let negative of x squared, or let x squared only, sorry, be equal to t. That means dx is t, or yeah, dx is t. Or let me use dt dx. Let me start side to not be a rush version. So that means, you know that dt dx
Yes.
will be equal to 2x, which implies that dt times 2x will be equivalent to dx. So what we're going to do now is we're going to substitute it into the equation. So now this becomes of e raised power minus x all square times.
Ufon, can you look at the substitution again? I think there is a small typo somewhere. So if dt dx is 2x, then the x,
Yes, dx is equal to, okay, sorry, 2x of dt over 2x.
Exactly.
Sorry,
yeah.
So dt over 2x. So now what we're going to do here is that we see that the limits are from negative infinity to infinity, right? And the gamma function works from 0 to infinity. So what we're going to prove here, we're going to use a proof here to show that this whole function, as you can see here, is similar to another function. This entire function, this function here, we can have it similar to another function. So I shall prove this earlier. I don't know why I did not. So we know that there's a special theorem that helps us know that for even functions, let's call an even function f of x. Let's say f of x is even.
What do we mean by saying that f of x is even? What does it mean to us? Because, you know, some of us here are not mathematicians. We are economists.
Okay, so
yes.
F of x is even means that f of x is the same thing as f of minus x. So here now, we know that e raised to power minus x squared is even because x squared, because of this x squared here. So for whatever value of x I put, maybe -1, it's still going to give me the same value as 1. So for memory, we know that this is even, this is an even function. So there's a theorem that says that for f of x, an even function, the negative infinity, the proper integral of negative infinity to infinity is equal to 2 times the definite integral of 0 to infinity of f of x dx.
Do you mean like symmetric
Symmetric
functions?
Yeah, symmetric functions. Yes, symmetric across the y-axis. If I'm correct.
Yeah.
They're symmetric across the y-axis. So yeah, that's what I mean. Symmetric functions across the y-axis. So this is the proof that we're going to be using. That for all even functions, the integral from minus infinity, the proper integral of minus infinity to infinity of f of x dx is equal to 2 times the proper integral of 0 to infinity of f of x dx. So now
this looks very interesting. Can you prove? Do you know how to prove this result? Can you prove this result? You know how to?
Okay, I should prove the result.
No, I mean you cannot prove it. We are almost running out of time. We have like 3 more minutes left. But do you know how to prove it?
Yes, I do know.
Okay, so please continue.
Okay, so once we do this, we can apply this here. So from factoring out everything here, we know that.
Okay, thank you everyone for attending the presentation. We appreciate the time, the 1 hour that you have spent listening to Ufonobong, and we have come to the end of the presentation. I want to thank, there are a number of people who have contributed to Ufonobong's growth. We have Chika Odinaka, who has been teaching him LaTeX, and he has improved significantly in the LaTeX. So thank you, Chika Odinaka. We also have Mebratu. Mebratu is Ufonobong's math teacher. He teaches Ufonobong between second year and third year level mathematics courses. So thank you very much, Mebratu. And then we have Inland, who teaches Ufonobong physics and some engineering things. Thank you very much. And it's the culmination of your efforts that has led to this successful outcome. Hopefully, we'll be discussing with Dennis, has just spoken not too long ago. So Dennis is a professor of statistics at Michigan State University. We'll be discussing to see if Ufonobong's paper can be published in some sort of journals. Let's see what is going to happen. But thank you so much, everybody, for attending. And we launched the undergrad, high school to undergrad program not too long ago. So if you know of talented students whom you think would benefit from our program, please ask them to reach out to our coordinator, Abayomi, who will be able to accept students.
Is he in high school?
Yes, Ufonobong just finished SS3 2 months ago, high school. Yeah, so high school level. So maybe I didn't mention that Ufonobong finished WAEC in July. Is it NECO that you did in July, or some of those our local?
No, it was NECO in July.
And so NECO, so he finished high school about 3 months ago, and he's 16 years old. And he's on the undergraduate admissions market. He's trying to get into hopefully a university where he can study either economics or math or engineering. And he's one of the people that we are training for the future to join our pipeline. As I said at the start of our talk, we are trying to get much, much, much younger people. In addition to the more mature people that we have, we are trying to get much younger people that we can train to the level that we want. And then they are going to join the pipeline of the people who will be doing a PhD in finance, economics, or related areas in the future. All right. So thank you all for coming to the presentation, and have a nice day.
Thank you.
Thank you.
Thank you.